Alright, so ChemActivity number 21 is getting into covalent bonds and dipole moments. And basically we're trying to look at and ask the question, are all bonds created equally? So the first thing that we want to look at is classifying bonds as polar or nonpolar. What we're basically looking at is the distribution of electrons. And one of the things that we can look at is partial charge, but we can use electronegativity. Well, we've already done partial charge calculations, but we can use electronegativity values to determine whether or not a bond is polar. Okay, so now one of the things that we first want to do as a basis for comparison is look at something like H2. Okay, H2, that molecule looks a little bit like this. Now when you think about the distribution of the electrons between these two hydrogens, well, they are equally distributed between these two hydrogens because of the fact that their electronegativities for both hydrogens are 2.30. Both of these hydrogens want the electrons the exact same amount. Okay, now if you compare that to something like HCl, now we've got a molecule that looks like this, where we have an electronegativity difference of 2.30 and 2.87. So this shows that this chlorine within this molecule wants those electrons a little bit more. And so what we would do is we would define this as being, well, slightly polar. Okay, and now whenever we're looking at this molecule and classifying it as polar, we can classify partially positive side and the slightly more negative side. And so we use a denotation system that looks like that. So that's a positive basically on this end, on the left-hand side of your arrow, and an arrow end pointing to the chloride. So where your partial negative charge is. Okay, so this shows you partial positive and partial negative charges there. Okay, so basically if you see an electronegativity difference, then you're looking at, an electronegativity difference between two atoms within a single bond, that would constitute a polar bond. Now, bond polarity is one thing, but molecule polarity is a completely different thing. Well, maybe not completely different thing, but it's related. It's a little bit more involved. So if we take something like HCl, this bond is polar, and we would say this molecule is polar. Okay. Now if we take something like CH4, okay, well, our electronegativity difference between carbon and hydrogen is going to be 2.54 and 2.30. Okay, so you could say that there is a partial positive end and a partial negative end because of the fact that we have one atom that's more electronegative than the other. Now, what does that look like with respect to our vector? It looks a little bit like that. We have partial positive end going towards our carbon. Okay. Now, how does that shake out whenever we look at the overall molecule? Well, when we look at the overall molecule, what we have is a collection of 4 of those same bonds. Okay, so now what we have is a bond like that, another bond like that, another bond like that, and finally our 4th bond like this. Okay, so we have 4 bonds, and where are they all going? They're all going in the same direction. So it's safe to say that this is a bond which is polar, because we have an electronegativity difference, but this molecule is non-polar. For some reason, I always imagine that I think about it being basically like a game of multiple games of tug of war going on at the exact same time. We have these partial positive charges that are pulling the electrons, but they're basically canceling one another out. So bonds cancel So these bonds cancel one another out, and so they make this, what would otherwise be a polar molecule, a nonpolar molecule. Okay, now the last part about molecule polarity and bond polarity is this classification, or this kind of designation as to the quantification of this polarity, or this, of this polarity. We have what is known as a dipole moment. And this is the vector quantity which looks at the magnitude and direction of a bond. Now this kind of is displayed as mu, which is your dipole moment, is equal to the magnitude of two charges and multiplied by d. D is the distance between your two charges. Okay, so we're able to look at the magnitude of the charges, or magnitude of the two charges and the distance. So if we look at something like HF versus HCl, the dipole moment for HF is 1.82 D. D is the units, the Debye, which is the units for measuring dipole moment. HCl has a dipole moment of 1.08 D. Okay, so one of the ways that you can kind of look back at that is, what is the difference between your electronegativities? The electronegativity difference between HF and HCl, they are going to be different. 4.19 minus 2.30 versus 2.87 minus 2.30. Now you can't use those numbers to simply plug that in and there you go, there's your dipole moment calculation, because it's a little bit more involved than that. It takes into consideration partial charges, but it does give you a little bit of a perspective. Now, one of the things that's important about this is whenever we look at a molecule like water, H2O, water is a polar molecule because of the fact that it has these two lone pairs of electrons. Now, these two lone pairs of electrons, as we previously looked at, they're going to occupy a big chunk of space. And what they're going to do is they're going to push these hydrogens downward. So those hydrogens are not directly opposite one another, so those polar bonds would not cancel out. So water is an example of bonds are polar and the molecule is polar. Okay, so now when it comes to drawing the dipole moments, what we need to do is we need to recognize, okay, what are our arrows signifying our poles? Okay, so water, we've got an arrow going inward towards our oxygen, because our oxygen is more electronegative. And we have this positive end to indicate where our individual hydrogens are. Okay, so we have a partial positive charge. Oopsies. These ends, and partial negative up here. Now what's important about this is, well, where does that actually show? The key factor here is this is a vector. And so what we need to do is we need to signify where that dipole is, or where that dipole moment is. And what we have is, we have one signifier for this molecule. We have our partial positive charge basically halfway between our two hydrogen atoms. So this is displayed in figure 3 of your ChemActivity number 21, but that is the rationale for that. We have our green arrows are indicating the polarity of each bond, but this bluish, navy blue colored vector is showing the dipole moment for the overall molecule. One of the things that we always think about with respect to polarity and dipole moments is the magnitude of that dipole moment. So you can look at HF versus HCl, and you can look at the electronegativity difference as kind of an indicator of what to expect with respect to the magnitude of that dipole moment. So I would say that HF has a greater dipole moment than something like HCl due to the fact that, well, it has a greater electronegativity difference. Now, in addition to that, you could think about a nonpolar molecule. Does a nonpolar molecule have a dipole moment? Dipole moment. Well, let's think about this. This is multiple bonds that are going to cancel one another out. So a nonpolar molecule has no dipole moment. If it has polar bonds that cancel one another out, well then that's a good example of a molecule that does not have a dipole moment. Okay, well, I hope that was helpful, and yeah, I hope this is helpful, and if you have any questions, feel free to get in contact with me through email. Thanks, have a good one.